Hi guys. Today let's understand the prisoner's dilemma problem. So we've talked about Nash equilibrium and game theory, and we've started with initiating what game theory means and what the strategies in it are. And we also talked about the mixed strategies. Now let's come on to the prisoner's dilemma problem. Another problem with the Nash equilibrium of a game is that it does not necessarily lead to a Pareto efficient outcome. Consider, for example, the games depicted in table 29.4. We'll talk about this. This game is known as the prisoner's dilemma. The original discussion of the game considered a situation where two prisoners who were partners in a crime were being questioned in separate rooms. Each prisoner had a choice of confessing to the crime and thereby implicating the other, or denying that he had participated in the crime. If only one prisoner confessed, then he would go free, and the authorities would throw the book at the other prisoner, requiring him to spend 6 months in prison. We're going to watch at this in a table format in just a minute after we read through this. But try to take the intuition from here. So the first point that they've said is that if one of the prisoner is confessing to the crime, he would walk away, and the other one would be required to spend 6 months in prison, which is pretty intuitive in itself. If both prisoners denied being involved, then both of them would be held for 1 month on technicality, and if both prisoners confessed it, they would both be held for 3 months. The payoff matrix for the game is given in table 29.4. The entries in each cell as a matrix represent the utility that each of the agents assigns to the various prison terms, which for simplicity we take to be the negative of the length of their prison terms. Let's just have a look here. So, like we read, if one of them is confessing and the other one is denying, the one who confesses goes free and the other one has to spend 6 months in jail, and that is denoted as a negative of that number for simplicity. Whereas if both of them are confessing, then each of them have to face 3 months in prison, depicted as the negative of the term. And if both of them deny, they have to be held for 1 month for technicality, and hence each of their 1 month jail term is expressed as a negative of 1. Put yourself in the position of player A. If player B decides to deny committing the crime, then you are certainly better off confessing, since then you'll get off free. Okay, so let's talk about the position of the first player, which is player number A. If player number A is confessing, um, okay, let's talk about player number A first. What's happening is that let's assume that that player B is confessing the crime. Okay, so for player A, the better outcome is to confess as well. Okay, because he has a negative term of 6 months if he denies it, and he has a negative term of 3 months, which is if he confesses as well. So that's the case where he's going to be better off in case B decides to confess. If B decides to deny, uh, where do you think he'll be better off? He has a 0 day for confessing and 1 month for denying. He's better off confessing, right? So if B decides to deny committing the crime, then you are certainly better off confessing, since then you'll get free. Okay, so it's better that he confesses in case B denies. So this is going to be the outcome. Similarly, if B confesses, then you will be better off confessing, since then you get a sentence of 3 months rather than 6 months. This is what we discussed initially. So what player A has to do in case B is confessing is that he must confess as well. Then whatever B plays, A is better off confessing. So we studied both of these, and what we found out in the first case was when player B was confessing, then A was better off to confess. And the second, we discussed how he is better off confessing even when player B is denying. So for player A, whatever B does, it doesn't matter, he's better off confessing. The same thing goes for B. He's better off confessing as well. Let's check for B uh, now. Let's take another color. Okay. So talking about player B now, check if player A confesses and what is good for B in that case. So if player A is confessing, then if you check for B, we have -3 here and -6 here. So he is better off confessing as well in case A confesses. If you check for denial, uh, if you assume that player A is going to deny, what's going to happen? Check the payoff for B, which is 0 and -1. So he's going to spend 1 month in prison versus he's going to spend 0 months in prison, which means he is better off confessing as well. So basically, what at last we've come to be is uh, the case which was good here is confessing, and the case that's good here is confessing as well. Okay. Thus, the unique Nash equilibrium for this game is both players have to confess. Okay, so this is the Nash equilibrium. In fact, both players confessing is not only a Nash equilibrium, it's a dominant strategy equilibrium, since each player has the same optimal choice independent of the other player. Like we read that if it doesn't matter what B chooses, A is always better off choosing to confess. Okay, so it doesn't matter what the other person is choosing. So it's an optimal choice independent of the other players. But if they could both just hang tight, they would be better, each be better off. If they both could be sure the other would hold out, the both would agree to hold out themselves, they would each get a payoff of -1, which would make each of them better off. The strategy deny is Pareto efficient, but this is the strategy that both of them are better off playing. It's a Nash equilibrium. But if you talk about this one here, the one that they have right now is this one, which is confess with 3 months in jail for the both of them. But it's because they're not sure of what the other one is going to do. Because what if they confess and the other one denies? If that's the case for A, he has to spend if B is going to deny and A has to confess, that then he has to spend 6 months in prison, and same is for B, which is why they both think that they need to confess and they'll be better off without knowing what the other person is going to do. But in order to get to the Pareto efficient strategy, um, they need to both hold out and deny the crime. The strategy is Pareto efficient. There is no other strategy choice that makes both players better off. Okay, this is the best strategy called the Pareto efficient strategy because it makes both of them better off. While the strategy confess is actually Pareto inefficient. Okay, the problem is that there's no way for the two prisoners to coordinate their actions because they, if you remember, they're both being interrogated in different rooms. They're not sure what the other person's going to say, if at all. Because if, like I discussed before, if one of them confesses and the other one denies, then the one who's confessing is actually going to get a whole of 6 months in jail, and the other one is going to go all out, 0 months. But they don't know what the other person is going to do. So if each could trust the other, then they would both be made better off. The prisoner's dilemma applies to a wide range of economic and political phenomena. Consider, for example, the problems of arms control. Interpret the strategy of confess as deploy a new missile, and the strategy of deny as don't deploy. Note that the playoffs are reasonable. If my opponent deploys his missile, I certainly want to deploy, even though the best strategy for both of us to agree to not deploy. But If there is no way to bring a binding agreement, we each end up deploying the missile and are both made worse off. Okay. So it's basically just redefining this whole sect into a problem, an arms control problem of deploying missiles and not deploying missiles. We both end up deploying because we don't know if the other one is not going to deploy or is going to deploy, which makes us both to deploy. And it's actually a Pareto inefficient problem because it's making the both of us worse off. But only if we trusted or knew that the other one is not going to deploy, we would have not deployed as well, and there would be no issues. Same as a prisoner's dilemma, they would both get out with just 1 month. Another good example is the problem of cheating in a cartel. Now, interpret confess as produce more than your quota of output, and interpret deny as stick to the original quota. If you think the other firm is going to stick to its quota, it will pay you to produce more than your own quota, right? Because if they're going to stick to their quota, you can produce more and you can get more money. And if you think that the other firm will overproduce, then you might as well too, right? So if they're going to overproduce, then you might as well. The prisoner's dilemma has provoked a lot of controversies as to what is the correct way to play the game, or more precisely, what is a reasonable way to play the game. The answer seems to depend on whether you are playing a one shot game or whether the game is to be repeated an indefinite number of times. If the game is going to be played just one time, the strategy of defecting, in this example, confessing, seems to be a reasonable one. After all, whatever the other fellow does, you are better off, and you have no way of influencing the other person's behavior. That was it. I hope this was helpful.